In this video, we're looking at some more types of probability problems. We're going to start with events that involve the word not, okay? So we're talking about the probability that an event E will not happen, okay? And since we used this notation to represent the probability that an event E will happen, the probability that the event will not happen is going to have that apostrophe in there, which if you remember from previous sections, means that we're talking about the complement, okay, or not E, okay? Because the probability that something will happen and the probability that it won't happen have to add up to 1, the probability that something won't happen is going to be 1 minus the probability that it will happen. Now, as far as which of those we want to find, it just depends on the problem. One might be more convenient than the other. And maybe they're equally convenient, okay? So really it just depends on the problem. But what we're talking about here is, let's say with percent. We know that all of the possible outcomes have to add up to 100%. And if the probability that, the forecast says there's a 40% chance that it's going to rain this evening, well, that means the probability that it won't rain is 60%, okay, or 100% minus 40%. So that's really where we're going with the not thing here, okay? All right, looking at this first example, if 2 fair dice are rolled, what is the probability that 2 different numbers are shown? Okay, that 2 different numbers are shown, so that we don't have a 1-1 or a 2-2 or a 3-3, etc. Okay, couple ways to do this. We can look back at the dice chart, which shows all 36 possible outcomes, and we can count all of the ones that don't have a repeat in the number. Okay. Or we can say, let's figure out the probability that they do have the same number, okay? And then the probability that they have different numbers is going to be the complement of that event, all right? So I'm going to say, what is the probability that we have 2 of the same number showing, okay? And from that dice chart, I remember that I could have a 1-1, 2-2, 3-3, etc. Sorry, my pen is not very accurate here. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Those are the only options, okay? So there are 6 favorable outcomes of having the same number out of the 36 total options, or we could reduce that to 1/6. And that's the probability that we do have the same number. So if I want the complement of that, the probability that we have different numbers, okay, so different numbers, I'm just going to abbreviate that, okay, then that's going to be 1 minus 1/6, okay, 1 minus the probability that they're the same number. And 1 minus 1/6 means we have 6/6 minus one of them is 5/6, okay? And like I said, with this problem right here, since we're looking at a dice chart anyway, we could just count up all of the ones that have 2 different numbers showing. But some problems that may not be convenient. So if we look at this next example, now we have 3 dice that are being rolled, okay? And same thing, we want the probability that at least 2 different numbers show. So in other words, we want the probability that we don't have 1-1-1 or 2-2-2 or 3-3-3, okay? So here, I don't want to look at a chart of all of the different outcomes of 3 dice. In fact, I do need to know how many outcomes there are. So let's use the counting principle. So the first die, the second, and then the third. I know that I have 6 possible outcomes for each. So 6, 6, 6. I have 216 different outcomes for those 3 dice being rolled. Okay? Now, of those 216, I definitely don't want to go through, write them all down, or look at a chart and then figure out how many of them have at least 2 numbers that are different. So instead, I'm going to use the complement, okay? So again, what is the probability that they all have the same number, okay? And I want the complement of this, so actually, let me write that differently so I don't have to write quite as much out here. I'm just going to write, what is the probability they have or not the same numbers? Here, I'll write that. Not the same numbers. Sorry. Notation there really, the label there doesn't really matter so much, but I know it's going to be 1 minus the probability that they are the same, which is 6 out of 216. Because again, we could have all 1s, all 2s, all 3s, all 4s, all 5s, or all 6s. 6 out of 216 does reduce to 1 out of 36. So I have 1 minus 1 out of 36, which 36 over 36 minus 1 over 36 is 35 over 36. Okay? So again, here's an example where it's a lot more efficient to count the rest and then subtract that from the total to get the probability that we want. Okay? All right. So those are events that have the word not in them. Now we're going to look at probability involving the word or. Okay? So here we're still looking at a single outcome happening, but we want to maybe meet more than one condition. So it could be this or something else. Okay? Our first example says a card is drawn from a standard deck. Find the probability that it is a 7 or a 9. We may want to look at a deck of cards. If you're not familiar, then just Google deck of cards, and you can see plenty of images that have all 52 listed. Find the probability that's a 7 or a 9. Well, I know that there are 4 that are 7s. 4 out of the 52 are 7s. Okay? And there's another 4 that are 9s, one of each suit. Okay? So together, I add those and I get 8 out of 52, or I can reduce that by 4, and I get 2 out of 13. So the probability of a 7 or a 9, 13, not 3, is 2 out of 13. Another way, again, if I'm looking at a chart, is I could just count. There's a 7 of clubs, 7 of hearts, 7 of diamonds, 7 of spades, 9 of clubs, 9 of hearts, 9 of diamonds, 9 of spades. And so there's a total of 8 ways out of 52. And I see that that's the same thing as if I add the 2 probabilities of each of those individually together, I still get the 2 out of 13, okay? Another example with cards. Here, a card is drawn from a standard deck. Find the probability that's a club or a face card, okay? Well, if I'm looking at my deck of cards, I see that I have 1 full suit of clubs, so that's 13 out of 52, okay? And then I also have 3 face cards in each suit. The face cards are the jacks, the queens, the kings, not aces. Okay? So jack, queen, and king. So there are 12 face cards. Okay? And if I add 13 over 52 plus 12 over 52, I get 25 over 52, which doesn't reduce. So 25 cards will satisfy club or face card. But I have a little bit of a problem. Okay? If I'm looking at a deck of cards, there are actually 3 cards that satisfy both being a club and being a face card. Okay, because I've got a jack of clubs, a queen of clubs, and a king of clubs. And the probability of choosing those 3 cards is not higher than the probability of choosing any other card, okay? It's not like there's 2 of each of those. So really, I don't want to count those, okay? So I'm going to subtract 3 of those cards because, remember, the jack, queen, and king of clubs were counted in this fraction and in this fraction, and I cannot count them twice. So I need to take those back out, okay? Or in other words, I have 22 out of 52, which reduces to 11 over 26, okay? So my probability is 11 over 26, not 25 out of 52, okay? So let's talk about these 2 problems together. These are examples of what we call disjoint, okay, or overlapping sets, okay? And if we think back to what we've learned with Venn diagrams, we can get a pretty good visual representation of that. The first example with the 7 or the 9 was an example of 2 sets that are disjoint, or mutually exclusive is another term for this. It means they do not have any elements in common, okay? So no common elements. In other words, there's nothing that's counted as part of both groups. If we're looking at a Venn diagram, okay, our sample space is everything inside S here, and I've got all of the A options here, all of the B options here. There's nothing right here where they are overlapping, okay? So the probability of one or the other happening would just be simply the probability of the first plus the probability of the second, okay? But frequently, we end up with a little bit of overlap. Okay, so let me draw another Venn diagram here. A, B, okay, in our sample space, or our universal set. Doesn't really matter what letter we use there. And if they have any outcomes in common, whoops, missing a word there, let's add that, outcomes in common, then the probability that something will satisfy one or the other is the probability of A plus the probability of B, but then minus the probability of the overlap, which is the intersection. Remember, this symbol right here represents the intersection. Okay? So in other words, probability of A is going to be anything falling in this bubble. The probability of B is going to be anything falling in this bubble. Okay? But what we notice is that everything inside here was counted twice. And since each card, in this case we're talking about cards, since each card has an equal likelihood of being chosen, okay, we don't want to double count any of those possible cards. So we need to subtract what's in the overlap because it has been counted in both A and B. I don't want to subtract it twice. Okay, it still has a likelihood of being chosen, okay, and it still satisfies our condition. Like, I don't want to take out the jack of clubs twice for club or face card, all right, but I do need to take it out once so that it doesn't get counted as part of both groups, okay? So the important thing to remember here is that if there is any overlap, you need to subtract that overlap, okay? We need to subtract that intersection. Another example that involves that here, we've got ping pong balls that are numbered from 1 to 20, and they're shaken up in a bucket, and one ball is drawn. So there's an equal likelihood that each of the numbers from 1 to 20 gets picked. Okay? We want to know what is the probability that the number shown on our one single ping pong ball that's drawn is a multiple of 3 or 4. Okay? So to do this, we need to consider all of the numbers from 1 to 20 and see what multiples we have. So multiples of 3 are going to be 3, 6, 9, 12, 15, and 18. And then multiples of 4 are going to be 4, 8, 12, 16, and 20. Okay? And then we want to know how many are multiples of either of those. Okay? So let me write this out with probability. We want the probability of a multiple of 3 or 4. Okay? And according to this one right here, since we've got some overlap, I see a 12 in both of these. Is that the only? Yep, there's a 12 in both of those. We want to consider the overlap. So this is going to be, or the intersection. So this is going to be the probability of a multiple of 3 plus the probability of a multiple of 4. Okay? Minus the probability that it is both a multiple of 3 and 4. Now, we don't generally need to write this out right here, okay? But this is just helping me organize exactly what I'm counting, okay? Especially because I'm not looking at a Venn diagram. I'm just looking at a list of numbers. So the probability that we get a multiple of 3, well, there are 1, 2, 3, 4, 5, 6 numbers that are multiples of 3. Okay, and now it's not just how many ways, but remember we're talking about probability. So 6 out of 20. Okay, which by the way, that can be reduced, but I don't want to reduce these until I have added and subtracted everything I need to, because I need a common denominator in order to add and subtract anyway. So leave it as 6 out of 20. Okay, then multiples of 4. I have 1, 2, 3, 4, 5. So the probability of choosing one of those is 5 out of 20. But then we need to subtract the probability that it is both. And like I said, there's one number, the 12, that is both a multiple of 3 and 4, so we subtract 1/20th, its probability, and we get a total of 6 plus 5 minus 1 is 10 out of 20, which does now reduce nicely to 1/2, okay? So if you see something that says the probability of, and it gives an or condition, if something could satisfy A or B, whatever those might be, you need to double check, are there any elements in our possible outcomes that would satisfy both? And if so, we need to make sure we subtract those so that we don't count them twice.